Huygen's principle, and we're going to describe Huygen's principle and apply Huygen's principle to refraction. Okay, now light's been around, well, since the beginning of time. It's been studied for thousands of years, mainly because if you were to ask any human, just about any human would say if they had to lose a sense, sight would be the one they were least likely to want to lose. That's the one everybody wants to hang on to. Now, some Greek philosophers thought the light consisted of tiny particles which enter the eye to create the sensation of vision, and actually they weren't that far wrong. Others thought the vision resulted from streamers or filaments emitted by the eye making contact with an object. That has since been fallen by the wayside. Now, up until the time of Newton and beyond, most philosophers and scientists thought the light consisted of particles, and they were partially right. One Greek thought that light traveled in waves, and he was partially right too. One of Newton's contemporary, a Dutch scientist named Christian Huygens, which is the subject of this lecture, also argued that light was a wave. Now, the particle theory was supported by the fact that light seemed to move in straight lines instead of spreading out as waves do, but Huygens showed that under some circumstances, light does spread out, and other scientists found evidence to support the wave theory. The wave theory became the accepted theory in the 19th century. But the particle theory had not rolled over and died yet. Albert Einstein came along early in the 20th century and resurrected the particle theory of light. According to this theory, light consists of particles called photons, and these are massless bundles of concentrated electromagnetic energy. Scientists now agree the light has a dual nature, so both sides won, part particle and part wave, and light has a tendency to behave like waves when it travels in empty space, and like particles when it interacts with solid matter. And actually, in reality, you really need quantum mechanics to describe light. And that's unfortunately a topic that's not in this class. I wish it were because it's a lot of fun. Now, in the late 1600s, a Dutch mathematician scientist named Christian Huygens proposed a very interesting idea about light. There's a point source way off to the left here somewhere, way out there. Okay, and it's so far away that at this point, the light waves have spread out so much that they're basically wave fronts. And he said the light waves spreading out from a point source may be regarded as the overlapping of tiny secondary wavelets. So what's going on here is here's a wavefront, and along this wavefront, each point along the wavefront creates a new set of tiny wavelets. These overlap, and they create the next wavefront at a time t equals delta t. So every point on any wavefront may be regarded as a new point source of secondary waves. And this idea, the wavefronts are made up of their wavefronts, is called Huygens principles. And this concept can actually be used to describe phenomena such as refraction, reflection, diffraction, and so on. And we'll revisit this. Now, these drawings actually come from Huygens' book, The Treatise on Light. And of course, in those days, all they had for candles. But a candle, when you're far enough away from it, it's a point source. And every point on this candle flame is a glowing plasma. Candle is a plasma. And of course, it emits these little wavefronts, these little wavelets, okay? And these expand in spherical wavefronts. Each point on a spherical wavefront behaves as if it were a new source of waves, and this scores every point on this wavefront here becomes a new source of wavelets that make the next wavefront. So every point along this spherical wavefront, AA prime, is the source of a new wavelet. So here's a new wavelet. We're only drawing a few of them because it would just fill in so much. The new wavefront at BB prime can be regarded as a smooth spherical surface enclosing the infinite number of overlapping wavelets that started from AA prime. And BB prime will itself be a source of new wavelets that will form the next wavefront. And of course, these wavefronts all travel at the speed of light. Okay, now far away from the source, the curvature of the wavefront will flatten out, and the wavefront will appear to form a plane. So here's the wavefront with its little point sources, and here's the new wavelets and the new wavefront. Now, you can observe this sort of thing in waterways that are made to pass through a narrow opening. And you can make a water tank very easily. You can do this in the bathtub if you want. All you need is a ruler or something that can be moved back and forth and make waves, or dipped up and down. And you need a sort of a narrow opening. When these straight wavefronts, this ruler will make straight wavefronts, pass through an opening in a barrier, you get a wave pattern. You can sort of see it kind of designated here, and it spreads out. And you can sort of see how here's the point source, here's those little wavelets coming out. Every part of a wavefront can be regarded as a source of new wavelets. It becomes very apparent. You can kind of see this right here. And because these circular waves fan out on this other side past this opening. So here's a picture from above. When the opening is wide, the wavefronts just sort of come straight through without much change. there is some bending around the corners, and this is called diffraction. As the light encounters a sharp edge, it will bend around the corner. And there's evidence of there's those circular wavefronts. Now, as the opening gets narrower, if it's about the wavelength of the wave, less of the wave will get through. And the emerging wave, you can sort of see how if you made it narrower, brought these together, these two curves would come together to make a single curve. You kind of see that. So you can see that. You can also see here's the wavefront, here's a point source, here's the wavelet. Every point along a wavefront is the source of a new wave. And this law of reflection can be proven using Huygen's principle and can also illustrate refraction. Up at the top here, here's a wave coming in. It's going to reflect off of this surface. It's coming in at an angle like this relative to the normal. And part of the wave, of course, wavefront will encounter the surface first. It reflects. And each part of the wave that's reflecting now is a new source of wavelets. As this wave comes in here, more and more of the front gets reflected, produces this new set. And of course, the angle of incidence relative to the normal equals the angle of reflection relative to the normal. When a wave instead encounters a medium of higher index of refraction or different index of refraction, in this case, it's higher, the wavefront will encounter the medium at an angle here relative to the normal. And first one side encounters it and slows down, and each part of the wavefront becomes a source of new wavelets, and the whole thing bends toward the normal. We'll see that more later, right here. Okay, so we're going to derive the law of refraction from Huygen's principle, and you should have worked on this at home before the lecture. Okay, so if you look here, here are rays, here are the wavefronts along the rays, and each wavefront is a source of new wavelets, which are not shown here because the drawing would get too confusing, but those themselves create the next wavefront. The distance between these two wavefronts is one wavelength. This whole thing's traveling at the speed of light. It's encountering a medium that's denser, so it's going to slow down. Air has almost an index of refraction, almost 1, and glass is somewhere between 1.3 and 1.5. Okay, so when it starts encountering it, it's coming in at an angle relative to the normal. And when it starts encountering it, it starts to slow down. So these wavefronts kind of bunch up. Okay, because remember, this is the wavelength, and this is a snapshot. Even with each one of these is a certain delta t, certain amount of time that passes between this one and this one. And they slow down, so they come closer together. So we look at these two triangles here. Look at the two triangles. Time is, of course, lambda 1 over v1. And that, of course, is in the incident wave. That also has to equal, because the times are equal, lambda 2 over v2. And we can rewrite this as lambda 1 over lambda 2 equals v1 over v2. That describes how the wavelength slows down relative to the speed of the wave. Now, we look at these two triangles here. One triangle is HCE, okay, and the other one is HCG, and they share a common hypotenuse. Okay, so sine theta 1, which is this angle right here, is lambda 1 divided by HC, which is this length here, hypotenuse. Sine theta 2, which is this angle here, is lambda 2, that's the wavelength in the second medium, divided by that same hypotenuse for that second triangle. Now, we can combine these two and eliminate the HC. We can find out that sine theta 1 divided by sine theta 2 equals lambda 1 over lambda 2, and that equals, if you look here, v1 over v2. We also know from the index of refraction, the definition therein, that n1 equals c over v1, and n2 similarly is c over v2. Now we can substitute that in here and eliminate the c's, and we find out the sine theta 1 divided by sine theta 2 will be n2 over n1. And if we rearrange that, we wind up with the law of refraction. Thank you very much. Please don't forget to do your homework.